Hello, everyone. Welcome back. Today, we will look at some applications of exponential functions, and specifically growth and decay functions. So we want to be able to use exponential growth and decay models. We'll explain those in a moment. Also, we'll be able to find what's called the doubling time for exponential growth and be able to find what's the half-life for exponential decay. So let's look over here at the left and below. First, let's talk about exponential growth. So an exponential growth model is something that looks like this. Okay, in general. So let's depend on what everything is. So first off, your P0, that's what's called the initial value. That's the amount you're starting with, whatever it is you have. Okay. Of course, the E is the exponential base. K is what's called the growth factor here. K is positive. All right. And T in this case is time in some units. That could be seconds, minutes, days, weeks, months, years. It could be any of those. So basically, what it usually comes down to is here it says units of K are the reciprocal of those of T. So often we're given using something from what we're looking into or trying to investigate will somebody give us some idea then of what we want our units to be in. A lot of times it determines it in terms of K. It's like maybe, you know, um, growth so much per year, per day, something like that. Now, so this P0 is the initial, once again, this P0 is the initial amount. That's what you start with. And then essentially this entire exponent then gets larger and larger. Of course, exponential growth goes really fast after a brief period. And so this gets larger and larger. Now, an interesting thing about exponential growth, if it's just purely exponential growth defined by a function like this, is we can actually find what's called the doubling time, okay? The time it takes from the initial amount to double the initial amount, okay? And that time, called capital T, time, once again, time it takes to double from the initial amount is given by T, which is equal to the natural log of 2 over our growth factor K, okay? And that natural log of 2, of course, is a constant. Let's take a look over here and kind of explain first, before we actually work some problems, where this growth factor comes from, or where this doubling time comes from. We'll also talk about the half-life, which is related to this. Okay, so first off, let's start with our function. So this time, remember, we're starting with, on the right side, P0, which is our initial amount, times E to the KT. Okay, now if you want to know when it doubles, it has to be twice the initial amount, or 2 times P0. Okay, you want to find out how long it takes to get to this. Of course, as you can see, the P0s cancel out. We're left with 2 is equal to EKT. Okay, now when I take the log, or if you take any log, just take the natural log of both sides, since that's the inverse of E. And since these are inverses, these cancel out. We're left with ln of 2 is equal to KT. I'm sorry, well, let me go back and change something. So T, specifically, T was the time it takes to double. So let's put that as capital T here and here. Okay. Right. So specifically, that's the time it takes to double. Okay. And now we have this expression, natural log of 2 equals K times T. Just divide both sides by K. We get that T is equal to natural log of 2. Remember, natural log of 2 is a constant over K. Also, if you know the doubling time, you can also find K from this equation. Okay. So this is called the doubling time. And based on, and that's simply based on T, this time, and then K. So for the same K and T, this doubling time will always be the same. Now, we can also have, instead of exponential growth, we can also have exponential decay, okay? A function that decays quickly. So that expression is almost identical. So you can put both of them on the screen at the same time. The only difference here, everything else is the same, except now we have a negative in front of our K. We're saying our K is 0, K is greater than 0, K is positive itself. We have a negative in front. That's the only difference. And because that's negative, this becomes exponential decay, or a very rapid decay. Okay, we'll see some examples of that later. All right, everything else is the same. P0 is still initial value. Now the K is actually called a decay factor. Okay, and the units of K work the same way. Now we also have what's called the half-life, and the half-life is actually related to the doubling time, and we'll see it's actually given by this same expression. Okay, So the half-life, the time it takes for initial population, the P0, to reduce by half, and it's given by, as you can see, the same expression. Let's take a look and understand that. Okay, so this time is very similar. We'll see why I get the same thing. So let's get on the right side. We'd have our exponential equation, our initial amount P0 times e to the negative kt, since we are decaying. And here we once again using t for this half-life time. And what here, instead of 2 times P0, we're going to have 1/2 P0, 1/2 the initial amount. Once again, the P0s cancel out. So we have 1/2 is equal to E minus KT. Now, as we did over here, let's take the natural log of both sides. And since natural log and E are inverses, they cancel each other out. And I'm also going to do something else on this side. So 2, I can write 1/2 as 2 to the negative first. And then on this right side, we have negative KT. Now, the reason I did that, we can use the properties of exponents. So I can actually bring this constant down front as -1 times the natural log of 2 is equal to negative KT. As you can see, now if I divide both sides by negative K, as you see, this is going to become positive. We're getting exactly the same thing. So T is equal to natural log of 2 over K. So once again, from this, I can, if I know my decay factor or decay constant, sometimes called a K constant, I can find my half-life, the time for my half-life, or if I know my half-life, I can find the decay constant. Okay, now, the reason why these are both the same expressions is if we had the same functions here, okay, if these are exactly the same, except you have the same initial value, the same K, the same T, if the only difference is that we have a negative in front of this one and positive in front of this one, then basically this one in the same time, you get a doubling of this one or half of, you get a doubling of the initial amount here or a halving or half of the initial amount here. Okay, it'd be exactly the same time for everything else being the same, except the only difference between these two is this one being positive, this one being negative. Your T, your time for either your doubling time or half-life would be exactly the same. Okay. Now, let's take a look at some examples. And also, let's take a quick look at, let's go to Desmos briefly, take a quick look at some of these functions. So remember, if we have, and also talk about how we can change them, what changes these things. So let's do y equals, first off, let's start with just e raised to the, let's make k just e to the x, okay? In this case, our k would be x. So remember, this was an exponential function looks like, okay? And here we're focusing on, since we're thinking of t, or in this case, x is time, we're thinking of this as just forward in time. So we're starting at 0. So we're kind of ignoring what happens over here, okay? It's a very fast growth. So at initial time, initial moment, at time equals 0, you have the initial value. And then you see it grows rapidly. Now, let's change a few things. Let's see what happens. So let's put a couple of constants here. Let's put an A here and a B. This is a nice thing to do with Desmos. I can actually put sliders for these. What that means then is I can actually see what happens as I change these things. Okay. Now, so how can you increase the amount? Okay, for if it is exponential growth, how can you increase the amount? Of course, as time increases, that increases the amount, of course. Also, if you increase your initial amount, that will increase your final amount. See, it grows faster if I increase the initial amount. Okay. Back to 1. Now, if my growth factor, or something's called the growth constant, my B, which would be my K, if I increase that, see, it also grows faster. Okay. So the things that make it grow faster, of course, are things that make it grow in general, of course, time, as it proceeds through time, but also if you increase your initial amount, that will give you a larger final amount. And also if you increase what grows the most rapidly is this growth factor, okay, by increasing that. Now, let's just simply turn this around, make this negative. Okay, now we have an exponential decay. So once again, we're thinking about x, in this case, there's our t, time being positive, we're ignoring everything happens on this side, okay? Now, in the same way, if I want to, now there's actually things will be a bit different, okay? If I increase my initial amount, then actually I have a larger amount after a given time because I have a larger initial amount, okay? But if I want it to decay faster, then I increase my decay factor, or what's called my decay constant, okay? The bigger that is, the faster it decays. You see, it quickly goes to zero, larger that is, okay? So the main thing there is if you want to, if you're talking about reducing the amount, of course, time will reduce it. And actually, these go in, instead of exponential k, they both went the same direction. These go in opposite directions. If I increase my initial amount, then I have a larger amount later on. But if I increase my decay factor, then this decays really rapidly. Okay. Let's go back. Let's take a look at some examples. Okay. So first, let's look at exponential growth. Under ideal conditions, a population of bacteria has an exponential growth rate of 11.9% per day. Consider the initial population of 1,000 bacteria. The first is find the exponential growth function. So what we need to find then, we want to make our function look like this. So what we need then are P0 and our K. Now our P0 is given by initial population. So P0 is equal to 1,000. Now what's our K? Our K, this is given to us as a percent, okay? And so that's going to be, we'll change that to a decimal. I'm going to change a decimal, move your decimal place 2 places to the left. And so that's going to be 0.1179. So our function, P of t, is 1,000 times e to the 0.1179 t. That's our function. Okay, so this defines how quickly it will grow. Okay, once again, based on this initial amount and based on this growth factor. Next thing it says we want to graph the function. So we'll kind of do a basic graph here. We'll also do one on Desmos. Here's time. Here is population. Write that better. Okay. Now, of course, here at 0, 1, when e is 0 or t is 0, remember e to the 0 is 1. So when t is 0, we're going to have 0 and 1,000. That's our initial population. And then this is going to grow rapidly like this. Okay. And then we can also find for different values how much it grows after your t. Also, what's t in? Well, here, remember, it says this is growth rate of per day. So this is actually our units are this per day. I should have put that in to begin with. So that tells us that our time is in days. Okay. So as I said, often we get that from our growth factor, other factors. So it tells us what we're studying, what our time is in. And you need to make sure that your growth factor or decay factor is in that same, essentially that same units of time, except 1 over time. Okay. Now let's go to Desmos and take a look at this one. Let's actually get rid of these. So we have y equals 1,000 times e raised to the, here, I'm going to use parentheses to make sure, get everything 0.00, point. Sorry, I'm having trouble with my keyboard actually. So let me just erase that and start over. Y equals 1,000 times e, and I'll also use parentheses just to make sure this works right well. I'm sorry, I'm actually having trouble with my my keyboard. So 1,000 times e raised to the, in parentheses, 0.1179x. Okay. Now, Why we can't see it is because our initial point's at 1,000. So here we go. Okay. Yes, this is incredibly hard to see. So let me actually change this. Let's change my x-axis to, how about make it 0, say 0 to 5. That would be good. Let's start with that, 0 to 5. So I'm going to find this from 0 to 5. Okay. And my y, let's make it let's try 0 to 10,000. See how that looks. Maybe 5,000 then. We have to kind of play around with this. Okay, good. Now, so let's zoom out. Okay, now it doesn't look very exponential, but if we zoom out enough, we'll see that. Okay, now if we zoom back in, let's take a look. So once again, here at 0, so that's 0 and 1,000. So after 2 days, okay, it's increased to, from 1,000, decreased by about 266. Let's see what 5 days, how much is increased to. So 1803.67. So you see it's growing there. So it grows even after about a month. You see how rapidly it's grown from 1,000 up to about a month, then to like what, 30,000 or so. Yeah, so about 34,000. See how rapidly that grows. That's what exponential growth does. Okay, let's actually go back to our example. All right, this is basically what it looks like. Now, what's the population after 7 days? So the way we find that is just plug that into our function. Okay. So P of 7 is equal to 1,000 times E to the 0.1179 times 7. We can actually do this on Desmos. Let's go back there. I'm just going to copy this. Okay, and just put in 7. Okay, so after 7 days, after a week, approximately, let's put his whole numbers. So this is, remember, this is a used to be population of bacteria. So let's just call it, let's just round up just for estimating purposes, 2283. So approximately 2,283. Okay, then at 2 weeks after 14 days. Now, remember, this is exponential growth. So it's not simply going to double in this amount of time. It's going to be larger than that. So 0.1179 times 14. Okay, let's do the same thing. Yeah, 5,000, approximately 5,210. Approximately 5,210. Okay, so you can see how rapidly that's growing. Okay, after initial population of 1, just after 2 weeks, you got 5,000. So that's pretty rapid. Okay, now find the doubling time. So our doubling time, we use this formula. So T is equal to the log of natural log of 2 over K. Once again, K is always put these, if you're given something as a percent, always put as a decimal in your equations. So 0.1179. And we can also do that on Desmos. So just do natural log ln of 2 divided by 0.1179. And so the doubling time is about 5.789. Okay. Now, let's check that to make sure that's right. So let's just take this, okay, and plug that in approximately. So about 5 point, we'll do it exactly, we'll get an idea. So about 5.879. Yeah, 1. So you get more, do it closer to 2,000. So yeah, that's the doubling time. So about 5 point, let's call it 5.88 days. And also, whatever your units of your time are, that gives you the units of your doubling time. Okay, about 5.8 days. Okay. All right. Let's take a look at another one. This one's a bit different. This one says the revenue from ebook sales, not including educational textbooks, accounted for about 5.5% of U.S. publishing sales in 2006. This percentage grew to about 22.6 in 2012. Yeah, assuming an exponential growth model, we want to find the value of k and write the function. Okay. Now, so let's understand what we're looking for. So let's look at our models. Once again, this is exponential growth again. So our model is going to be P of t is equal to P0 times e to the kt. Okay. Now, what is it we need? Well, we're trying to find, so what don't we know? We don't know. Let's plug in what we do know. Okay. Now here, these give us percentages, and we'll write them also as decimals. We can think of this as our starting, although it's a starting percentage, we can think of this as actually a starting amount if you want. Okay. So our initial one times 0, we're thinking that is 5% or 0.005. Okay. Now, the current time we're trying to get to, or just our P, okay, at the end is 22.6 or 0.226. Okay. And what else do we know? We know our time. Okay. The time it took for this to happen is 2012 minus 2006, which is 6 years. This will tell us what our t is going to be. It's going to be in years. Okay. Now, what we're going to do is plug all that in. We do that, we have 0.226 is equal to 0.005 times e to, let's put it as 6k, 6 times k, okay? Since t is 6 times k, we need to find is want to find k. Actually, I made a little more space here. All right. So first off, let's divide both sides with this 0.005. And that comes out to 45.2 is equal to e to the 6k. Okay. Now, like we did before, I found the doubling or half lifetime. Let's take the natural log of both sides. So the natural log of 45.2 is equal to the natural log of e to the 6k. And these, since they're inverses, cancel each other out. And so then we have the natural log of 45.2 is equal to 6k. So I'm kind of running out of space. Let me actually, let's see, go right here. Yeah. See if I can move that up. Nope, not that. There we go. Okay. All right, need a little more space here. Maybe a bit more as well. Let's just go ahead and just move that. Okay. So we have that then. Okay. So, and now divide both sides by 6. So k is equal to the natural log of 45.2 divided by 6. Let's find that. Okay, let's use Desmos, or yeah, let's just use Desmos for that. Natural log of 45.2 over 6. Use your graphing calculator. So the natural log of 45.2, and that's divided by, divided by 6. And that's approximately, I'll do 3 decimal places, 0.635. 0.635. So k is equal to 0.635. So our exponential model then is P of t is equal to and P of 0 here was, remember, so P of 0 is 0.005 times e to the 0.635 times t. Okay, that's our model. All right, so now we want to use that in a couple examples. So I'm kind of having to adjust my spacing here, but that's okay. Right, it says estimate the percentage of publishing sales, of the ebook sales in 2009 and 2010. Okay, I also should say one more thing for this model here, then t equals 0 in 2006. That's important, okay? So you have to judge everything from that, all right? So for, obviously, 2009, t is equal to 3. And so what that's going to be is p of 3 is going to be 0.005 times e to the 0.635 times 3. Okay, let's do that also in Desmos. 0.005 times e raised, and we're going to use parentheses, so 0. I think it was 637. Double check that. Or 635 rather. Times 3. Okay, and so that is going to be 0.03. Remember, this is a decimal. I have to change the percent. Let's do the to 4 places. So 0.336, 0.0336, 4 decimal places. Okay, that's equal to 0.0336. And this percent, then, that's going to be 3.36%. So in 3 years, it's grown from 0.5%, 0.05, to about 3.3%. Okay, then let's do for the other one for 2010. Okay, so obviously in 2010, t is equal to 4, so do exactly the same thing. Okay, t of 4 is equal to 0.005 e to the 0.635 times 4. So we'll just go back to Desmos, and what we'll do is we'll actually just replace the 3, with 4. Okay, and let's do 4 decimal places again, 0.0634. Okay, 0.0634. And so that's going to be as percent is approximately 6.34%. Okay, as you see, pretty rapid growth, pretty quick growth. All right. Now, one thing also is worth mentioning here. Notice we're asking what were the sales in 2009, 2010. With a model like this, you shouldn't really use it too much beyond the data. Okay, what I mean by that is it goes from the data we have is from 2006 to 2012. Okay. Now, the dangers in trying to project it out too far, maybe like to 10 years in the future, is as fast as it's growing, eventually you're going to get over 100%, which won't make any sense. It won't make any sense from a numerical standpoint, since it can't be over 100%, but also, as you imagine, it's not going to, ebook sales not going to take over all book sales. That would mean to be responsible for the revenues of all book sales in 10 years, which doesn't make any sense. So keep in mind, a lot of times the mathematical models you make, this may be a youthful growth model between these 2 years, 2006 and 2012, but eventually it's not going to be exponential all the time. That's something we have to be careful about. Okay. In fact, let's go back and take a quick look and do that quickly. So what if we do like 10 years times 10? Let's do something larger than about 20. Let's go back to 10. Yeah, so actually at 10, remember this is a decimal. So we'd have 280, after 10 years, you have 286%. 10 years from a 2006, you have 286%, which wouldn't make any sense. So that's one thing about, as you may learn about modeling or trying to use functions like this to predict things or to estimate things. A lot of times you have to be careful about trying to predict too far beyond the data you have, because it may not really fit that data. Okay. All right, let's take a look at that. Okay. Now let's see what's next. Number 3. Okay. Now this one is about money. Okay. For initial investment of $10,000, find the resulting amount after compounding continuously for 5 years at 0.5% interest annually. Okay. Now this model we can actually use for what's called continuous compounding. So if you may have studied other kind of math involving interest rates, or interest rates and growth versus interest rates. And there are different kinds of exponential functions involving compounding. You can compound per month or per year, per day, per month, per week. But the limit, the fastest you can get, is what's called continuous compounding, which uses this formula here. Okay, let's figure out what we have. So what's going to need to find out what our P0 are and our K are to predict this. Now it says the initial investment. That's anytime it says initial, that's our clue. That's the P0. And P0 is 10,000. Okay. What's our K? Well, that's our interest rate as a decimal. So it's 0.5%. So you have to change that to a decimal. So we'll calculate the last one. That's going to be 0.005. Okay. And that's going to be annually per year. Okay. That also tells us in what our time is going to be. And our time then is going to be in years. Okay. Now I want to find the resulting rate after 5 years. So our T is going to be 5 years. I want to make sure your interest, your K and your interest rate are the same units of time. Okay. This is 1 over year. Then your time needs to be in years. Okay. So let's plug all that in. And that's going to give us our P of 5 years. Okay. Is going to be 10,000 times E to the 0.005 times 5. Okay. Let's go back to Desmos and we'll figure that out. Let's go down here. So we have 10,000. That's our initial amount. Then E raised to, once I use parentheses, 0.005 times 5. And that is $10,253.15. It's around the nearest cent. Okay. Now, that's not an incredible amount of growth after 5 years. Of course, it's not a very large interest rate. Okay. But, yeah. So here, think about this interest rate. This one we just did. The reason it's such fast growth, that was basically a 63.5% growth rate. This is a 0.5% growth rate. Okay. But still, our final amount after 5 years, the money that you've earned from that is $253.15. So 10,253.15. So your result after that is that amount. So what you've earned, once again, from interest is $253.15. Okay. Now, that's not that, as you see, that's not an incredible amount for that. What if we did that for like 30 years? Okay. I think this is a retirement account. What if we did this for 30 years? Okay. Still not a lot. Okay. But at the same time, that's a very low interest rate. All right. So the point is, though, the longer you leave it in, the more you get out, obviously. Okay. So even a low interest rate, that's still not a lot for that amount of time, but it is growth. At the same time, if you want a faster growth rate, you need a larger interest rate. Okay. Now, listen for problem 3. Let's find the doubling time. Okay. So the doubling time. Okay. To use this formula we have, so T is equal to ln2 over K, and K is 5. So just try that. You can do that on a calculator if you want, or in Desmos. I'll just use my own calculator this time. So try this on your own calculator. So the natural log of 2 oh, sorry. Let something look weird. Yeah. No, it's not 5. I'm sorry. It's K, which is over K. Sorry. And this is going to be the natural log of 2 over K, which is 0.005. Okay. There we go. Let's try that again. So find the natural log of 2. And divide that by 0.005. Okay. And so the doubling time, the doubling time is actually a long time. Okay. So in terms of years, this is about 138 let's just call it one place, 6 years. That's a long time. The reason why it's a long time is because our interest rate, our growth factor, is really small. Okay. That's the reason it takes such a long time. So if you had this if you're trying to grow, an amount for retirement, then obviously this would not be a good way to do it at this interest rate because the interest rate is so small. Okay. All right. Let's see what's next. So next, let me just move this down. We have more space. Okay. So this is another one about continuous compounding. If the current amount of investment is $10,000 after a doubling time of 6 years, find the annual interest rate K and the initial amount. Okay, so a few things going on here. So now the current amount, what does that mean? Well, the current amount, so if I said the initial amount, that would be your P0. So the current amount would just be your P. Okay, so P is equal to 10,000. So this time we're changing the idea of it. So 10,000. Okay, the doubling time, T is equal to 6 years. Okay, now we want to find K. Let's find that first. Okay, we can actually do that. Okay, so our doubling time equation is T is equal to natural log of 2 over K. Okay, now this time we want to find K, all right? This formula is given in terms of T, we want to find K. So actually we need to solve this for K. And one way we can do that, you can think this is cross multiplying if you want, okay? Actually, what I'm going to do is just something we can, anytime you have an equation, you can always just flip both sides. By flipping, I mean find the reciprocal of both sides. And that's an equivalent equation. So what I mean is, if T is equal to natural log of 2 over K, 1 over T is equal to K over the natural log of 2. Okay. That's an equivalent statement. I just took the reciprocal of both sides. Now, multiply both sides by the natural log of 2. Okay. And then we get, show that. So the natural log of 2 on both sides. Okay. It cancels out here, and we get that K, almost we turn it around, K is equal to the natural log of 2 over T. That's convenient. Okay. And so we do that then. And this is going to be equal to the natural log of 2 over T, which is 6. So let's find that. So natural log of 2 divided by 6 is, I'll do, say, 3 decimal places, 0.116. Approximately 0.116. Okay, so K is that. Okay. So that we found the interest rate. Now, how can we find the initial amount? All right, so let's find the initial amount. And once again, let me just move everything down here. I mean, the rest of this page for this. Okay. Okay, so now I want to find the initial amount. All right, how can we do that? Well, let's plug everything in. So now we have that P. So P, there's right as PTL is right as P is equal to P0 times E to the KT. All right, that's our general formula. Okay. Now let's plug everything in. What we have. So our current amount is 10,000. Okay, is equal to P0. That's our unknown, right? Then E to the K, which you just found is 0.116. And our T this time is our doubling time of 6 years. All right. So now just divide both sides by this. Okay. And we get that P0, which would be an arrow, P0 is equal to 10,000 divided by that. Let's go to Desmos for that. Okay. So we have 10,000 divided by E raised, so once again, I use parentheses. So 0.116 times 6. And the initial amount then for that is $4,985.76. around the nearest cent, round up, 4985.76. Okay, so once again, what that means is that if I put this amount of money in the bank at this interest rate, okay, and also say up here, let me say one more thing about K. So then as a percentage, then that would be 11.60% annually or per year. Okay. But this is also per year. All right. As our time is given in years, this is per year. So this is 11.6% annually, annual growth, which would be great if you can get a rate like that. Okay. So what this is saying is if you put this amount of money in the bank right now at this interest rate, then in 6 years, it'll double. Okay. Um, okay. Wait a minute. Hang on just a second. Let's see something. Um, yeah. So what happened is, yeah. So basically, it's double out. Initially, it should be actually, of course, 5,000 to be double. The reason it's not is because I rounded this off a bit. Okay, so 0.116. If I hadn't rounded it off and more accurate, then it would have actually be 5,000. Okay, but that's also something comes into play. So small changes like that, rounding things off, okay, can lead to differences. Okay, so we had a difference of about less than $14, but still, doubling time, it should go straight from 5,000 to that. So actually, if you put 5,000 in, actually at that rate, then we wouldn't be quite 10,000, be just a little bit less, or possibly just a little bit more. Either way, just depending on how you round that. Okay, so that's another thing about rounding. Be careful rounding. That can affect your final result. Okay, that gives you the basic idea. So if it's true doubling time, it should go from 5,000 to that. Okay. All right, last question. So now let's take a look at exponential decay, which works basically the same, except the only thing we're doing is just we have a negative here in front of our K. Okay. Now, this one says half-life of radioactive isotope is given in is 5.23 days. Now, radioactive isotopes, a lot of times isotopes in nuclear engineering, nuclear science, are a lot of times discussed by their half-life, because that's an indication of how radioactive they are. Okay. So usually something with a really quick, really rapid um, half-life, like a really small half-life like that, is typically really dangerous in large amounts because it decays, is giving off a lot of radiation. Okay. So generally, the longer the half-life for the same amount, the less radiation you get. Generally, that's kind of it's a bit, it's not quite true in every case, but that kind of gives you an idea. Okay. But typically, some of the longer half-life is usually less dangerous than the shorter half-life for the same amount. All right. Now, let's say find the decay rate. Okay. Well, once again, we use the same formula we did for the doubling time. So, except this time we could use the half-life formula. It's the same formula. Okay. So the half-life is equal to 5.23 days, as it says. Okay. So, what that is that's T is 5.23 is equal to ln2 over K. So I want to find K as we did a minute ago. Let's do the same thing we did a minute ago. So let's flip this. Okay. Let's take the reciprocal of both sides. So 1 over 5.23 is equal to K over ln2. Multiply both sides by the natural log of 2 to get rid of it. On this side, let's cancel out. We get that K then is equal to the natural log of 2 over 5.23. And then either use your calculator or Desmos to find that. I'll just use my calculator. And so natural log of 2 divided by 5.23. Okay. And that's equal to, I was going to approximating, I'll go to 4 decimal places this time, 0.1325. Okay. That's my K. And this is also then, since my time was given in days, my half-life, this is per day. Okay. Just remember, so your units of time and your units, and it should be reciprocal units of your either growth constant, growth factor, or decay factor. Okay. The last thing I want to do is find for initial amount of 10 kilograms this isotope, find the amount left after 20 days. Okay, so once again, what we have then is our formula is P of t is equal to P0 times e to the negative kt. All right, let's see what we have. So I know that P0, or initial amount, when time it says initial, that's usually the first amount, is 10 kilograms. Okay, I know what K is. K is what we just found. K is equal to 0.1325 per day. Okay, then time is at 20 days. So T is equal to 20 days. Okay, just plug all that in. And so then P of 20 is equal to 10 times e to the negative 0.1325 times 20. Okay, so let's plug this into our equation. Now let's also kind of get hopefully a good idea of what is going to happen. It's interesting about the idea of a half-life. Okay, so our half-life is about 5.23 days. Okay, now, so what that means is this half-life is constant. So after 5.23 days, I should have half of what I start with. Okay, half of 10 kilograms, which would be 5 kilograms. Then in another 5.23 days, I should have half of that again, only 2.5 kilograms. Then half of that again in the next 5.23 days. So basically, we're going through not quite, in 20 days, we're going through not quite 4 half-lives. So should it being about, we'll see what that's going to happen when we actually do this. So let's plug this into Desmos. Okay, so just 10 times e raised, so let's know for future negative, 0.1325 times 20. Okay, and it's about 0.7. Okay, so remember, this is not a percent, this is actual value. So let's do 3 places, 0.707. So 0.707 kilograms. So that's quite a reduction. So 0.707 kilograms. We started out with 10 kilograms and we're left with less than 1. Okay, so since we've gone through a little more than 4, or not quite 4 half-lives. Okay, so first the half-life reduced from 10 to 5. The second half-life went from 10 to, in fact, let's just write this out the side. So how do we explain this? So after 1 half-life, okay, we have 5 kilograms. Okay, after second, by second mean the second half-life, we're taking half of that again, which is going to be 2.5 kilograms. Okay, after third half-life, okay, so that's going to be 2.5 divided by 2, which should be about 1.25. Okay, after third half-life should be 1.25 kilograms. Okay, then divide that by 2 again, and that after the fourth should be 0.625 kilograms. You notice we have a bit more than that because we didn't go, because it's it's not 5 days, but 5.23 days. So it didn't go quite 4 full half-lives, but you can see how fast, how quickly that decays. And that's a very large decay factor. Like I said, a pretty quick as far as a half-life, that's a small half-life, which means it decays really quickly. Okay. And basically, is something radioactive going to go up a lot of radiation. So that would most likely be really dangerous to be around if you were close to it. Okay. So let's review what we learned today. Looked at some applications of exponential functions, specifically exponential growth and exponential decay. Okay. Exponential growth model. So we start with the initial amount P0, then K is our growth factor. If it's or in exponential growth, or if it's an exponential decay with a negative out front, it's the exponential decay. And then T, and once again, The units of K and T are linked. So whatever T is in, whether in days, seconds, minutes, hours, days, whatever, then your units of your growth factor or decay factor are 1 over those same units. Okay. Then the doubling time or half-life is actually given by the same formula. Okay, it's the doubling time, that's the amount of time it takes from your initial amount, whatever it is, to double. And then your half-life is the time it takes in decay for that initial amount to basically become half, reduced by half of what it was before. We're going to look at some applications where we actually use these ideas to solve some problems. Thank you. Have a good day.